Welcome to this lecture series in linear algebra. In this lecture, we'll learn the connection between solving linear equations and what we have discussed so far. And let us recall just what we need. In fact, let me just state what we need. So we need to know about the matrix representation of a linear map. So given a linear map between two vector spaces over the same base field, of course, if it is a linear map, then they have to be vector spaces over the same base field. And if we choose bases B and C of V and W respectively, then we can make a matrix which is the matrix of T with respect to the two bases. And let me not get into the details of this. This is what we discussed in the previous lecture. Okay. So let's get started. First, we will discuss this notion of coordinate representation of a vector. So, fix a vector space V and fix a basis of it. For a vector V, we define the following. We define this thing, which is also a matrix of dimensions n cross 1, where n is the dimension of V, n is the dimension of V. So it has n rows and one column. And if F is the base field, so this vector space is over F. I haven't written it. All right, so this is a matrix of the sort which is defined as this thing. Yeah, it took a lot of time. So that thing where what are these alpha i's? You write the vector V as the linear combination of V1 up to Vn in this manner. So I'm just deliberately writing it vertically. Right, so any vector V in the vector space V can be expressed as a linear combination of the basis vectors. The scalars that we obtain, we just arrange them in a column and we get an n cross 1 matrix. So this is the coordinate representation of the vector V with respect to the basis B. Okay. Right. The coordinate representation of the vector V with respect to the basis B. And again, if we were working with this space, so if we were f to the n, and we were given some vector V in, well, either we write capital V or f to the n, doesn't make a difference. So in that case, we may not write anything. We may just write mv to mean the coordinate representation with respect to the standard basis. Standard basis. Right? So in coordinate spaces, we have a natural basis, and hence this is not ambiguous. Okay, all right. Now here is a very simple fact. We have two vector spaces over the same base field F. We have a basis B for V, basis C for W, respectively. And we have a linear map from V to W. Then for any vector V in the domain of T, we can easily prove this. The matrix representation of the image with respect to the basis of the target space is same, not the main, I should say the coordinate representation. This is a vector, so the coordinate representation of the image vector is same as the matrix representation of the linear map times the coordinate representation of the vector that we started with. And this is just your matrix multiplication as we defined it. And this is compatible because the number of columns here is same as the number of rows there. So this is just an exercise in unraveling the definitions. You use the definitions of these things and you get exactly this. So the proof of this is an exercise, but this is an important fact. Okay, so now we come to our main concern, linear equations. So what do we mean by a linear equation? A linear equation over the field F, so F is some field, is defined as, so this is an equation of the form where these are some scalars or elements of the field F, and these are some unknowns. So you may call them variables. And in this list, beta is also there. So these are some fixed things from the field F, and these are our unknowns. Okay? Sorry about that. So for example, this is a linear equation over the reals. Let me give some space. So surely you have seen linear equations before in some context somewhere in high school, and this is just rewriting that. All right, now a system of linear equations over the field F is basically a collection of linear equations, is a bunch of linear equations. In the same, so every linear equation that we say will have the same unknowns. I will write it, is a bunch of linear equations of the form, of which form? Of this form. Right, so the first one is a linear equation. Here when I write alpha 1, 1, it's not alpha 11, it's alpha 1, comma 1, but I do not like to write that comma. Similarly, this is alpha 2, comma n. So there are n columns and m rows. Okay, and the unknowns are the same. So the unknowns in the first equation are the same as the unknowns in the second equation. Okay. I mean, even if the unknowns are not the same, you can make them the same by appending zeros as coefficients. So these are also called coefficients. So anyway, a system of linear equations is just a collection of linear equations. More than one or even one. Okay, nothing very interesting going on so far. But the question is, how do we solve? What can we say about the set of solutions of such a thing? And we will be able to comment on the qualitative behavior using linear algebra. How to exactly find these solutions, if there are many solutions, how to find all of them or something, that is not of our concern at the point. Can we qualitatively say something about the solutions? Maybe there is no solution. That can happen. Easily you can write down system of equations where there are no solutions. For example, this is a trivial system with no solutions. So clearly there cannot be any solution to this system. So there may be no solutions to a system of linear equations. There can be a unique solution, and there can be infinitely many solutions. So this has no solutions. Then you can have unique solution. So why does this system have unique solutions? Why does this system have a unique solution? Simply because these represent two lines in the coordinate plane which are not parallel, and two distinct lines can intersect only at exactly one point, and therefore there is a unique solution to this system. So here you get unique, and to get infinitely many solutions, this is one such example. And here you have infinitely many solutions you can verify. So this is something that we can comment on using linear algebra. All right. So what is the connection? So first of all, yeah. So we have some given system of linear equations. Note that this can be expressed very nicely in the matrix language as follows. We have this matrix This is an M cross N matrix, I think. N columns, yeah. And then you have this N cross 1 matrix containing the unknowns. And this is equal to the thing on the right side. So this horrible thing is same as this horrible thing. And this is just an exercise in matrix multiplication. So once we have this, now we can create a linear map whose matrix representation is this. And this, and we can write down a vector whose matrix representation is that, such that a equation in linear algebra will be equivalent to this equation. So here is what we will do. Just define a map T from this space to that. So everything was happening over the base field F. Define T as the linear map such that the matrix representation of T, and since we are working with coordinate spaces, we need not specify any special basis. We are working with the standard bases. So the matrix representation of T is same as this matrix. And if you're thinking as to why should such a linear map exist, just think about it. All you're doing is you're specifying the behavior of T on every individual standard basis, and once you specify that, there is a unique such linear map. So there is a unique linear map with this property, and let W be an element in F to the M. So wait a Right, so here I've made a mistake. This is an M. So sorry about that mistake. So W be a vector, or rather the vector, such that the matrix representation of W is, or the coordinate representation as we have called it, is this thing. And now the equation here, or the system of equations here, is equivalent to solving the following. Find a vector X such that this happens and take its matrix representation or coordinate representation, and you will find a solution. And conversely, every solution will give you a vector like that. So the connection is very, very straightforward. Instead of solving this matrix equation, you may solve this linear algebra equation. And the difference between the two is rather subtle. All you do is just take the matrix representation of both the things with respect to the standard basis vectors and use the theorem that we stated, this guy. And you will see that the two are exactly the same. Okay, so that is the connection with linear maps. Perhaps it is not very illuminating at this point, but let's see an application. So we have a system of linear equations. We call it a homogeneous system if these things are all zero, right? So one solution to this system is already the all zeros. If you substitute each xi as 0, then of course that's a solution to this system. And now basically all you're asking is, in the linear algebra language, so let T be a linear map such that the matrix representation of T is the one coming from the alpha ij's, right? So solving the above system now, solving this system is equivalent to finding the kernel of T. Solving this system, let us call it star. Solving star is equivalent to finding the kernel of T. Okay. And immediately, therefore, we conclude. So here is a fact or corollary if you want. If n is greater than m, then the system of linear equation, then the system star has infinitely many solutions. Now, this is not a surprising fact because if n is greater than m, then the number of equations is smaller than the number of variables, so you expect infinitely many solutions. But this is something that we can derive using linear algebra, because once you have a linear map and n exceeds m, then the dimension of this space is greater than the dimension of that space, and therefore the kernel of T has to be non-trivial. You can use rank nullity if you like. So the kernel has to be non-trivial, and hence it has to have infinitely many solutions, provided, well, of course, F is an infinite field. So yeah, I should say that F is an infinite field, only then I can make the statement. So let's say F is an infinite field here, assuming. So for example, if we were working over the real numbers, then this comment is true. So immediately using linear algebra, we can see this. All right, lastly, let's comment on a general system. So again, we have a general system of linear equations. These are not necessarily all zero. Then again, we have the linear map as previously. Right, we have this linear map, and WB in the target space. The matrix of W is the one coming from beta j's. Okay. So what we are trying to find is, we are looking for the vectors in the domain such that this happens, right? And now suppose you are able to find one solution. Maybe there is no solution. If there is a solution, if let's say x naught is a solution, then the set of all solutions is precisely x naught plus kernel of T. Right? And this is from linear algebra. So if x naught is already a solution and x is another solution, then you take the difference between these two equations. One equation is already here. So if you just take the difference of these two equations, you will see that x minus x naught lies in the kernel of T. And if x minus x naught lies in the kernel of T, then of course Tx will be equal to W. So once you have one solution, you can nail down all the other solutions. And again, if n were greater than m, this would mean that there are infinitely many solutions, where again I am assuming that the base field is infinite. So if there is one solution, there would be infinitely many solutions, assuming n is greater than m. And again, this is something that we deduce from linear algebra. So I do not want to formally write down these statements. One can make various statements here. If T is invertible, then blah, blah, blah. All right. As of now, I can just... so yeah, before I say this course is not going to be about matrices, even though perhaps that is what motivated the study of linear algebra. We will not be looking at things under the lens of using the lens of matrices. We will be taking more conceptual and somewhat more abstract approach and prove concrete things using that. To be able to solve such equations is of course important. There has to be some method that furnishes us all the solutions. So you can look at Gaussian elimination. Just do a quick Google. And you can also use softwares to solve such things. So you can look at Sage or MATLAB or something, where I'm pretty sure they, under the hood, use Gaussian elimination. So yeah, this was something to be done. We needed to discuss matrices and linear equations, but that is not the focus of this course. Alright, so with that I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.